We discussed speed and velocity in our previous video, but to really complete our understanding of motion, we need to introduce the concept of acceleration. I found that many students new to physics often get the concept of acceleration and velocity mixed up. So I'm hoping that if we go through it slowly, I can help you distinguish between the two. Let's start with an example. Imagine you're trying to decide between purchasing these two vehicles. Your concern is not the fancy style and feature of the car. All you really care about is you want to get from one place to the other. I know that's hard when you're looking at a picture of two very different cars, but try to keep that in mind. Just think of this only in terms of getting from one place to the other. Let's start with the Ferrari. We find that the car can go an impressive 0 to 60 miles per hour. Our car down here, turns out, can also do 0 to 60 miles per hour. This concept is change in speed. If my primary concern is getting from one place to another, then I definitely need a change in speed. However, they both can handle the same change in speed. So really, if you think about it, is there any reason, other than, again, ignore all the fancy features, is there any reason to choose the top expensive car over the more affordable lower car? There is, right? If we look further, it turns out that the Ferrari can go from 0 to 60 miles per hour in 3 seconds. The car in the bottom here is about 12 seconds. The new idea we've introduced is time. When you combine a change in speed with a time, that's what we call acceleration. Here's another example. Imagine you have two cars and they're going to race over a short distance. They both start from rest. One car accelerates to 50 kilometers per hour. The other car accelerates to 60 kilometers per hour. Which car won the race? What do you think? It's tempting to say that the faster car won, but really we can't make a claim based on the information that was given. What is it that we're missing? It's time. We need to know how long it took for those cars to reach the speeds and how long the race actually lasted. Notice that in this example, we're again discussing a change in speed and a time. Before I give you a formal definition of acceleration, please read through this question and answer it for yourself. Do take this one seriously. It's going to be important that you understand this. On this question, it's very common for me to see B as the most popular choice. And that makes sense because in everyday conversation, that's how we use the word acceleration. But this is a physics class, and in physics, the answer is D, all of the above. This is important. Remember that acceleration, as I talked about before, is a change in velocity. Well, velocity can be a slowing down, a speeding up. When I've asked this question in the past, it's been very common for me to see the most popular answer as B. And that makes a lot of sense. In everyday conversation, that's exactly how we use the word acceleration. But this is a physics class, and in physics, acceleration actually means all of the above. So pay attention to that. When an object slows down, we say it accelerated. When an object speeds up, we say it accelerated. When an object turns or makes any kind of change in direction, we say it accelerated. That's not how we usually use it when we're just talking outside of a classroom, but that's how we're going to use it in this class. So it's important that you understand that and start to accept that. We're going to define acceleration as the rate at which velocity changes, or in other words, how quickly velocity changes with time. In physics, usually our main focus is to take a conceptual definition like this and convert it into a mathematical relationship. So we're going to start with the definition of average acceleration as the change in velocity divided by the time interval. I need to emphasize here the word change. Velocity changes, change of velocity. Change is the key to understanding acceleration. Acceleration is not equal to velocity, it's equal to the change in velocity. So because it's so important for this concept, change is going to be the keyword for our Canvas video quiz for May 13th. This is going to be a short quiz, pretty easy. Acceleration can actually get pretty complicated, so we're going to start with the basic idea of constant acceleration. Constant acceleration is, of course, an acceleration that doesn't change. So if acceleration is constant, it turns out that the average acceleration is just the acceleration. Or another way to say that is this average acceleration is equal to the instantaneous acceleration. So there's no reason to distinguish between the two because they're always the same. Here's an example. This is the information from my previous slides. Now we're going to assume constant acceleration, and we're going to go ahead and calculate the acceleration for these two cars. I'm going to start by taking that definition from the previous slide and writing it in a little simpler notation. So this tells me that acceleration is the change in velocity over the change in time, and remember we're discussing constant acceleration. So for this problem, the change in velocity is a difference. So I need to take the final velocity, which was 60 miles per hour, and I need to find the difference between the starting velocity, which was 0 miles per hour. And it's important to understand that it's the change in velocity, not the velocity over time. So the interval of time is 3 seconds. So this would be 20, if I do the math, miles per hour per second. These units of miles per hour per second aren't usually used, but I just want to stick with the basic concept of acceleration, so I won't try to convert that into anything else. But notice that it's a speed on top in terms of units per second. So each second the car is changing by 20 meters per hour. In the bottom case, we have a similar thing on top, 60 miles per hour minus 0 miles per hour over 12 in this case. So that would result in 5 miles per hour per second. So each second this bottom car is only changing its speed by 5 miles per hour. The Ferrari apparently has 4 times the acceleration. So even if you're restricted to the same top speed, the Ferrari is going to get you to that top speed much faster, so you're still going to go places faster. I want to do a couple more problems. In this case, imagine you are driving in your car at 45 kilometers per hour for 3 minutes. What is your average acceleration in units of kilometers per hour per minute? I realize these are kind of funky units to use, but I don't want the math to get in the way, and in order to convert those to better units, we'd have to do some more math. I'm actually going to start this one by showing you what not to do. I see this all the time where a speed was given, a time was given, I'm actually going to start this one by showing you what you shouldn't do. I see this a lot where a speed was given and a time was given. Accelerations related to speed and time. So we simply take the speed, divide it by the time, and that gives us a result that has a number and units that match what they asked for. So we circle that and move on. See if you can spot the error and why you should not do it this way. Okay, so the issue is that acceleration is the change in velocity divided by the time it took to change. So look back in the problem, and where does it discuss how the speed changed? Short answer, it doesn't. It just says the speed was 45 kilometers for 3 minutes. That implies that the speed never changed. So down here, if we're going to do this properly, what we should say is that we ended at 45 kilometers per hour. And we're going to minus, because we need to find the difference in velocity. I'm going to minus what I started with over the time. Sorry, that's minutes. And that gives me 0. So if there's no description of a changing velocity, then your acceleration has to be 0. This problem is going to show us what we were missing in our previous example. You're driving in your car at 45 kilometers per hour. You slowly increase to 50 kilometers per hour over 5 seconds. What's your average acceleration in units of kilometers per hour per second? First, I want to point out that slowly increase, that's really just code for constant acceleration. That's important because constant acceleration is just going to be the change in velocity over time. Our change is going to be 50 kilometers per hour minus 45. And that's all over 5 seconds, which gives us so apparently our acceleration was just 1 kilometer per hour per second. I apologize for the bad handwriting. It's difficult to draw on a computer when I can't actually see what I'm doing. Here's an example that will hopefully demonstrate the difference between velocity and acceleration. In this video, we're going to watch a race between a jet, a car, and a motorcycle. The recording, unfortunately, is not very good, but it's a good example. Here I'm recording a recording, so it might not look very good. So I've included the link if you want to watch it for yourself. Okay, so we have a motorcycle, looks like a bullet bike style, a car, I believe that's a Porsche, and a jet. Which one do you think is going to win the race? Let's check it out. All right, so who won the race? Well, it's a question of at what point are we ending the race? You could at some point say that the motorcycle won. Let's go back and find that. Right there. In this image, if it'll let me show it, there we go. In this image, the motorcycle is clearly in the lead. So if the finish line happened to be right here, the motorcycle would have won. Short time later, the jet clearly overtakes the motorcycle. So if the finish line was there, the jet certainly wins. And even though it's not winning, the car does eventually overtake the motorcycle, so it would come in second place, depending on where we ended the race. So the thing I love about this video is it shows that velocity by itself isn't everything. Acceleration by itself isn't everything either. The motorcycle clearly accelerated the fastest. That's why it took off so quick. It was limited by its velocity. Given enough time, the others were able to overtake it. So that's why they're two separate concepts, but yet together they describe the motion completely. One last question for you. In this situation, I have the Earth going around the sun, and we're going to assume that the Earth follows a perfect circle with a perfectly constant speed. In real life, it's not exactly like that, but it's actually pretty close, so this isn't a bad example. So in this situation with a perfect circular path and a perfectly constant speed, my question is the Earth accelerating? The answer is emphatically yes, it's accelerating. Remember that acceleration is a change in velocity. Velocity needs a description of speed and direction. Here the speed is staying the same, but the direction is changing. So if the direction is changing, it's definitely accelerating. I'm going to go ahead and end here. In the next video, I'm going to cover a very popular example of constant acceleration known as free fall.